This is Santanu Banerjee, head art
Yeah,
scientist.
Shantanu, please.
I am pleased to introduce Professor Sheth. He is an alumnus of the department and he did a MSc and PhD in this department. He is a specialist of flat basalt volcanism. He has extensively studied the basaltic rocks around Mumbai and in Maharashtra region, particularly the Deccan Traps in Western India. Even he has visited many places to see these rocks, including Hawaii, Andes, Easter Island in Pacific, and Barren Island. He goes to field, observe volcanic rocks and volcanism physically, and interprets the geochemistry and tectonics of volcanic rock sample. He has received many awards like National Geoscience Award, PRL Award, and IIT Bombay Young Investigator Award. 2020 is going fine with him as he has received both teaching and research award. His book on a photographic atlas of flat basalt volcanism contains more than 500 color illustrations with explanations. This unique book illustrates varied geological features of flat basalts, including landscapes, lava flow morphology, structures formed by the lava flow transport, and many other features. He is likely to show many of such exciting field features. With that, I request Professor Seth to please give his talk.
Thank you. Professor Sheth, please see the time regulations, 12 minute talk and 3-minute question answer, please.
Okay, thank you. Thank you for this honor, first of all, and thank you, the committee, for this recognition. I would like to thank my head, Professor Banerjee, for the introduction. I'm a geologist who works on volcanoes, and I'm happy to be able to talk to you very briefly about my research work and my research love. So the slide shows you India's Barren Island volcano, highly active volcano in the Andaman Sea, where I have worked for some time. One moment, please. So what are volcanoes? Volcanoes are the vents where magma inside the earth comes out. Okay? So what is magma? Magma is molten rock which exists inside the earth at a high temperature. And this magma comes out of volcanoes either as lava flows, which means liquid condition, or pyroclasts, which means hot rock fragments. So this is the most active volcano in the world today, Kilauea volcano in Hawaii. And this picture shows you a typical situation at Kilauea volcano, where this is the active vent, and you have the fire fountain, which is the lava coming out of the vent, and then flowing as a stream or as a river of lava. That's the lava flow. And of course, there's an ash plume, very fine ash, sub-millimeter size ash, which rises to a very which rises to a considerable distance of kilometers into the atmosphere. And then there is the ash blanket in front of you, which is the
Can you make it full screen, please? You may make it full screen.
Oh, one moment, please. I need to.
Anyway, please go ahead then. This is visible. Yeah, it will be better. That's
okay, thank you. So what are the factors which control volcanic activity? So this is the subject of physical volcanology. There are many parameters which control volcanoes and volcanic eruptions. Parameters include the amount of magma which is present under a volcano, the rate at which it is being supplied to the volcano, then what are the stress fields which are acting on the crust on which that volcano sits, etc., etc. But one of the very important parameters is volatiles. Volatiles which are dissolved in the magma at the site of origin of the magma. So what are these volatiles? They are mainly H2O and CO2, and they make up only a few weight % of magma in terms of mass. But they are disproportionately important because they control volcanic behavior in a major way. So if you see the photograph on the left, it is a familiar situation where we open a bottle of any carbonated drink such as Coca-Cola, and there is fizzing because the dissolved CO2 escapes because of decompression. This CO2 was stored in a dissolved state inside the water or your drink, and then it was in solution. And because you opened the cap, there was decompression, and the solubility of the CO2 was minimal at atmospheric pressure now. So the CO2 came out, yeah, in the form of bubbles. In the same way, magmas at depth contain dissolved volatiles, CO2, H2O, fluorine, chlorine, many gases. And these volatiles come out in the form of bubbles when the magma has come near the surface or when it has erupted at the surface in the form of lava. So this is what you see in the picture on the right side. This is basalt lava, which is frozen now. So it is molten at a temperature of 1200 degrees centigrade when it erupts. And the dissolved gases come out and they leave these cavities. And these cavities, of course, do not close because the magma has, the lava has become solidified. So the cavities are preserved and they are known as vesicles. But cavities are formed from escape of volatile bubbles because the lava is fluid. And the lava is fluid because it has a low silica content and a high temperature. So my point is on decompression, vesiculation, which is the escape of dissolved volatiles. Volatiles were dissolved at depth and they escape on eruption. This is extensive in fluid magmas, which means magmas with low SiO2 content and high temperatures. For example, basalt, which is fully liquid at 1200 degrees at 1 atmosphere pressure. And basaltic eruptions are commonly effusive. Effusive means quiet, non-explosive eruptions. So here you can see a lava flow, active lava flow on Kilauea volcano, 2002 photograph. You can see red lava in the center. So you are able to go very close to the active flow front and even take a sample of the red lava on your geological hammer. So this is possible because the lava has already degassed extensively. So what is this basalt lava? We are all familiar with basalt lava because most of our Maharashtra and Madhya Pradesh, Gujarat are covered by these lava flows of basalt, ancient, 65 million years old. This is the most volcanic rock, most common volcanic rock on Earth and all terrestrial planets. It is everywhere in what we call as black granite, our kitchen platform. It is nothing but basalt. So the moon, if you look at the moon at night and see all the dark areas, they are all basaltic lava plains. Similarly, Mercury, Venus, and Mars, they contain vast basaltic fields. So volcanism is very, very important process of planetary evolution, chemical as well as thermal. Now, what happens with viscous lavas? So even if they come close to the surface, they cannot decompress because the lava is very viscous. And it is viscous when it is high silica, which means there is a lot of polymerization between silicon and oxygen units, and it is at a lower temperature. For example, the types of lava known as dacite and rhyolite, they are liquid at 850 to 900 degrees centigrade compared to basaltic lava, which requires 1200 degrees to be molten. So as this cartoon shows you, volatiles are able to escape easily and freely from a basaltic lava, which has 50% silica by mass, whereas volatiles are not able to escape from a high silica, highly viscous lava, such as rhyolite, just 76 weight% silica. And therefore, these volatiles are trapped for a long time until the breaking point comes. And then you have something like this. Okay? You have a huge explosion and an eruption plume in which the magma itself is fragmented uh, into blocks and fine ash. And this fine ash can be carried to great heights, such as 20 kilometers is a common height that this jet will be sent into the atmosphere. So it is common that silica-rich and volatile-rich magmas will produce explosive eruptions, unlike the basaltic eruptions, which are generally effusive eruptions, especially if the decompression was sudden. So this was a classic eruption in May 1980 in the western USA, Mount St. Helens. There are volcanoes which are mixed. They produce both explosive and effusive eruptions because of different magmas being supplied to the vent of the volcano at different times or even together. So India's own volcano, Barren Island in the Andaman Sea, is of this type, is highly active, especially since 1991. So it was sleeping for about 150 years up to 1832. From 1832 to 1991, there is no recorded activity of this volcano. From 1991, it has become highly active. It stands about 350 meters above sea level, and it rises more than 2 kilometers above the sea floor. That means it was a submarine volcano which started growing on the floor of the ocean, the Andaman sea floor, and then at some point, about a million years ago, it broke the surface, the sea surface. And now it is an emergent volcano. So this is one of the pictures I took during a field trip. And this is another view taken at a different time. You see the terrible lava flows of Barren Island volcano. Very, very difficult place to work. There is nothing there. And of course, the terrain is very, very hostile, very, very difficult. But scientifically, it's a superb, it's a fantastic place. So this is how lava flows frequently look. And then this is how, standing on the coastline from the active cone 1 kilometer away, you can see blasts, explosive blasts. So the fine ash which is produced from the explosion is carried to a height of a kilometer, a couple of kilometers. So you can see that the ash plume expands continuously because it heats the surrounding air and entrains the air inside it, and therefore becomes larger and larger. So it's like a cauliflower shape, expanding and rising ash plume. And then you see that after a few seconds, the ash, which is farther away from the eruption plume, starts to fall back on Earth. So
Last
much
two
of this
minutes,
ash will
Professor.
go
Last
into
two
the
minutes.
sea. Excuse me?
Last 2 minutes, please.
Sure. This is the other active volcano in the Andamans, India's possession, again, Narkondam, which is a corruption actually of Narakundam, which means hell pit, and it is sleeping. There are no historical eruptions of this volcano. There is no active monitoring being done by any agency in India of Narkondam or Barren Island. Actually, it's a bigger volcano than Barren Island. So we collect volcanic rocks from different volcanoes and volcanic areas, and then we bring the rocks back to the lab and we analyze them for chemical composition. Maybe we make very thin slices of the rocks and study them under the microscope, which tells us a lot of processes which have occurred. The mineral composition, the chemical composition, and the processes which occur in volcanoes. And everybody knows about granite. It's an igneous rock. It's a volcanic rock which forms in the roots of volcanoes. And when you have granite exposed at the surface, it tells you that there would have been volcanoes, ancient volcanoes standing there, which have been removed subsequently by erosion. So granite is very abundant all over India. And take, for example, the 140 million year old Ladakh granite. This is Shanti Stupa in Leh, sits on granite. Or go to the Aravalli range, Rajasthan and Gujarat, and then it's full of granite bodies which have been intruded into the crust. So granites solidify into the crust. They do not erupt, but they are the roots, as I said, of volcanoes at the surface. So these are 750 million year old granites. So in India, the rock record goes back to about 3.5 billion years. So India is one of the oldest continents on Earth. And the Deccan Traps are flood basalt lavas, which currently occupy 500,000 square kilometers. Originally, they would have covered more than 1 million square kilometers. And this is where I work mainly. Each 1,000 cubic kilometer lava flow, so very big lava flows, released, these are estimates, 10 gigatons of CO2 and 10 gigatons of SO2, all from one eruption. So there would have been hundreds of such eruptions at that time. So there is no surprise that this volcanism coincides with major biological mass extinction involving the dinosaurs, famous dinosaurs. That's the Cretaceous tertiary boundary mass extinction, which occurred 65.5 million years ago. So the questions I work on are why and how did the huge lava flows form in the first place? How did they erupt? How did they move from place to place? How did they solidify? These are some very interesting questions I have been studying and which I continue to study in the future. So this is Mahabaleshwar, and then everybody has been to Mahabaleshwar, Matheran, and these are all lava flows, 65 million years old. This is the book which covers the topic in detail, Photographic Atlas of Flood Basalt Volcanism. Talks about global flood basalts, including the Deccan Plateau flood basalts. Kindly see it for more information. This is the book which I self-nominated for this award, and I'm pleased and grateful that you have provided my work and this book the recognition. Thank you.